Hi scholars! Today we will talk about how to prove sequences converge. We'll start by defining what it means to converge to a limit. A sequence Sn of real numbers converges to a limit S provided for all epsilon greater than 0, there is a natural number n such that the absolute value of Sn minus S is less than or equal to epsilon for all little n that are at least as large as big N. Okay, that sounds pretty abstract. Let's check out what this means with a picture. Suppose Sn is given by 1 minus 1 over n, which converges to 1. Along the x-axis, we show the index n for each Sn. Along the y-axis, we show the value of Sn. We use a green bar to show the interval from 1 minus epsilon to 1 plus epsilon. What we want to know is how big n has to be to make all the numbers in the sequence from then onward be contained in the interval. Here we see Sn is within epsilon of the limit when n is at least 4. And so here the big N we could pick in the definition would be n equals 4. Note, however, big N often depends on epsilon. To see this, consider a different value of epsilon. Say epsilon equals 1 over 20. In this case, we still get convergence, but it takes more steps for Sn to get within epsilon of the limit. Let's zoom out and think about a typical proof structure. We start by stating the definition of what must be shown. Then we identify relationships between that definition and other known quantities. We conclude by combining these relations to verify the properties in the definition hold. That is a general way to think about it. Now let's make it more concrete for introductory sequence proofs. First, we can write out the shown phrase. We start by letting someone hand us an arbitrary epsilon. If we can find a big N for that epsilon, then the definition will be satisfied. Next, we play around with inequalities to find an upper bound that we know how to work with. We then show the definition holds by making this upper bound less than epsilon. Alright, let's walk through an example together. Suppose I need to show Sn converges to 2 when Sn equals 2 times n squared over n squared minus 2n plus 2. The first step is to paste in the phrase we just talked about. Step 2 is to observe we can use algebra to rearrange Sn minus 2 to 4 over n minus 1 plus 1 over n minus 1. Since 1 over n minus 1 is positive, we can bound this whole thing from above by 4 over n minus 1. Then we can use the Archimedean property of R to find a big natural number m. In step 3, we rearrange and combine these inequalities to show the absolute value of Sn minus 2 is less than or equal to epsilon. Picking n equal to m reveals this is precisely what we wanted to show. Let's visualize our argument, say with epsilon equal to 1/3. We make a plot like before, but this time we add a plot of the bound 2 plus 4 over n minus 1, and see that Sn is always between 2 and our bound. Here we can pick big N to be 13. That's all for today. You can check out more proof examples in the lessons for our course at www.typal.academy.